But this standard Big Bang model already had problems with it. And so we need to talk about that. Okay, we still got half an hour till I have to end this lecture. Okay, problem number one is the age of the universe as measured by the Hubble law disagrees with the age of the oldest globular clusters. So if H is 70 and we're at critical density, that implies the universe is only about a little more than 9 billion years old. Again, let's go back. Oops, too far. Too far. Here. So if the universe undergoes this kind of curvature, it means that the beginning of the universe is earlier than, what would be a straight line constant velocity. And so here, more density means more density in dark matter, all the way up to closure density, means that the universe actually begins earlier. Not as early as this red one here, but you get the point, okay? More curvature means the universe started younger. Well, that's a problem because we've already age dated the globular clusters and we know stellar evolution very well, we think. And it's pretty hard. The globular cluster age people, they're very diligent, hardworking people. And they said, you know what, we can't give you 9 billion years. No, these are 12 and a half, 13, 13.1, 13.2 even billion years old. I'm sorry, you're going to have to just deal with it. You cosmologists are going to just have to deal with it. Okay? So, how are we going to deal with it? Well, the type 1a supernovae look like they might help solve it because these are visible from so far away. We could really check the expansion rate of the universe going back not just to the local galaxies with their Cepheids, but all the way back to most of the way to the beginning of the universe, or at least halfway. And that's enough. So, I mean, obviously the pictures look pretty ratty when you're looking at type 1a supernovae that are this far away, but that's okay. All you really need, you need to get a spectrum, and you need to see their maximum brightness. If you can get that, you're in business. So this slide, I mean, I like that all these points lie on top of each other, but it's kind of a complicated diagram to explain, so I'll just say that this is really telling us that the type 1a supernovae really are all alike once you've corrected for their different metallicities. So, again, I kind of left the project there with Joel's group in 1996 and a half, 1997. Early 1997, I developed osteonecrosis. I quit all research except in my own medical situation. I'm spending all my time going up to UC San Francisco and camping myself in the cellar down there where all their journals were and learning everything I could about the biology of cartilage and everything else. Meanwhile, what was happening was the video you guys are going to see at 7:30, and that is they discovered that the universe is not slowing down like we thought. It's accelerating. Now, Brian Schmidt, you'll see on the video, when he first saw that the data indicated this, rather than be elated that he had discovered an incredible new property of the universe, he was, as he said, horrified. So I think what's admirable is that, horrified or not, he stuck with it and is like, okay, you know what? We really want to know what the truth is. This is what I love about hanging around scientists. You don't see that attitude around politicians or priests and religious people. It's so wonderful, anyway, to be around. People actually want to get it right. We really want to know what's the actual truth here. Now, luckily, there was another group that was doing the same kind of work, led by Saul Perlmutter. And so it's kind of, I can imagine what the conversation was really like, is they kind of, were starting to talk to each other, and nobody really wanted to admit that, I got these crazy results that can't possibly be right. But they sort of both kind of inched towards it, and they both realized that, you know what? Oh, thank God. we're seeing the same thing. And then it was like confession time, okay? And then slowly they realized that, this is actually really fascinating. This is actually great. This could be, I mean, if you're seeing the same thing, this could be really true. And then what does that imply? And the more we looked into that, the more we realized that, this solves all our problems. This is not a horrifying thing. This is a great thing. Now, there's a problem. We've got to account for it. Why? Why is the universe accelerating? It requires some kind of energy density in empty space. It turns out if you pack energy into empty space, perfectly empty space, that will have a negative gravity. It will cause space to expand all by itself. In this case, then, carrying its frame of reference and the mass that's in it with it. So this term was actually invented by Einstein long ago, the cosmological constant. We talked briefly about it when we got to our chapter on general relativity. That he thought for a moment it was his greatest blunder when Hubble showed the universe was expanding, and he didn't need this constant thrown in to just try and keep the universe from recollapsing on itself. And so he threw it away, but in fact, it turns out not to be his greatest blunder, but his greatest triumph. I mean, could you imagine being so smart that even your greatest blunder is like 100 years ahead of your time? And I mean, I could only dream of that situation. Okay, so here's the thing now about this aspect of space. If space is expanding, then the energy contained in that space is also expanding. So it doesn't dilute away like matter, little nuggets of condensed things within that space. That would dilute away as there's more and more space between the matter nuggets. But no, this is space itself that has this property. And so the more it expands, the faster it expands. And the faster it expands, the more it expands. And it's a kind of a runaway process. An amplifying feedback, as we in climate science would say. So as the universe expands and gravity's grip weakens in increasing distances, it becomes more and more to be dominated by the unchanging expansion force of space itself. Okay, so is that the way of it? Is that really the way the universe is? Well, it needed a name, so we call it dark energy. We don't know exactly why it's doing this, but we have some ideas. So there's not only dark matter, but now there's dark energy too. But that just increases the mystery, so it just makes it all that much more fun to be an astronomer. So this is kind of a drawing trying to show the way the universe would expand, and we thought it would be expanding but slowing while it was expanding. That's the old classical standard Big Bang, but now we see that the universe is not the old standard Big Bang, but it's got this cosmological constant, and therefore the universe is accelerating as it expands. Now here's what that buys for you as far as our first cosmological problem. There's H today, okay? So there we are now. So the slope of that line locally is fit very well. We know what that is, and so all these curves fit to it. But now if you put in a differing amount of this dark energy, you see that it changes how old the universe is. The universe traces back to a different time, and it's farther back than you would have gotten with no dark energy. See? There's the 9 billion years that we were stuck with and we were agonizing about because the globular clusters have got to be, younger than the universe as a whole, and they're like 12 or 13 billion years. Well, when we throw in the dark energy with a W of minus 1.0, which is what we got, the observations say, and that's just exactly what we want. It takes us right back perfectly to 13.72 billion years, nicely fitting with the globular cluster ages. So it resolves the age discrepancy, and now everybody's happy. The globular cluster age people are happy, the cosmologists are happy, everybody's happy. except maybe Luke. I don't know. So, yeah, it doesn't thin out as space expands. It stays the same density. So it comes more and more to dominate the universe. So 11.5 billion years ago, dark energy was just a little teeny sliver of the pie, and most of the matter energy content of the universe was in dark matter. But as time goes on, it comes to be a thicker and thicker slice, and now today, it's about 70% of the matter plus energy density of the universe. Now, I should tell you this. There's kind of two opposing aspects to this dark energy, whatever it is. It is energy. It is a positive energy. And as a positive energy, it has a gravitational effect. But because it's an energy in empty space, it has this negative gravity effect that actually wins that battle. But the point is that you really can add all of these together to get the energy density, matter plus energy density of the universe. And it turns out to add up perfectly. Okay, when Joel does with his Bolshoi, which just means big, Bolshoi simulations of a dark matter dominated universe, what you need to get the structure to look just like what we see in the real world, you can't, 95%, no. You only need like 25%. See? So maybe I'll tie in again why this dark energy solves the issue of clustering. So we thought we needed to solve clustering by having part of the dark matter be something that just refuses to cluster, namely the neutrinos. But instead, it turns out that the dark energy, which is forcing this new reacceleration of expansion, does the same job, and it does it without neutrinos. And in fact, so measurements today of the mass of the neutrino are not 5 electron volts. They're more like 1/100th of an electron volt, somewhere in that neighborhood. Okay, and if we go forwards in time, dark energy is going to come to be everything. So again, there's Darth Vader. It is our destiny. Now here's two opposing types of evidence that really nicely orthogonally intersect and give us a really clean estimate of the cosmic density of matter. And what do we get? We get about, sorry I can't draw a straight line, we get about 27%, I think is the favored number now. Drifts around a little bit as we get new satellite missions looking at the cosmic background. But that's about it. Okay? So galaxy clustering, this was the thing I used to be good at. Okay? That is telling us this. And the cosmic background radiation, which has lumps in it. But then the speed of the expansion, the other half of the situation, we got clustering, gravity, and we got the anti-clustering, the expansion. So that's told by the type 1a supernovae, and that gives you an arc like that. And so where do these both agree with the actual data? They agree in here. It nicely constrains where we've got to be, right about there. So we know we got 4% here. There's 4%. There's the ordinary matter. This part of it. The dark matter is all here. There's the ordinary matter, only coming out to here. There's the dark matter, and then all the rest of this, all the way up to 1, which is off the frame, is all dark energy. So yeah, it's a little embarrassing. We don't know what the dark matter is, and we don't know what the dark energy is. So 96% of the universe is made of stuff that we don't really exactly know yet. But it does fit observations perfectly. It gives us a zero energy universe, and we know how to create a universe like that. But it's actually all good. So is there any direct evidence for an energy density possessed by space itself? And the Casimir effect is related to that. So the Casimir effect is was predicted by this Dutch physicist way back in 1948. According to quantum theory, vacuum contains virtual particles, which are in a continuous state of fluctuation. And if you get two things very, very close together so that you begin to exclude whole de Broglie wavelengths between those two places, then you begin to exclude a certain amount of this vacuum energy, and therefore you'll create an additional pressure on the other side of it, and it'll cause kind of an artificial pressure difference that is the so-called Casimir effect, and we see that. It's a quantum thing. I don't want to get too lost in quantum mechanics here, so I'm going to march on. Nice little electron micrograph of how you do that, how you measure it. These are little deflectable, bits of metal, and there's a little BB. It's not, I mean, it's way smaller than a BB, but it's kind of like that, and it's under a pit here. And by, the space available here is different than the space that's available out here, and so that excludes some wavelengths, and therefore there'll be less energy down here, and therefore this thing's going to feel a net force downwards that it wouldn't have felt without this quantum Casimir effect. An energy density in the empty space itself.